Yeah, thank you for the invitation. And it's my pleasure to give the presentation at the first AI summit. And today's presentation title is A Vision and Language Approach to Computer Vision in the Wild. And you may see the presentation of the same title on the internet before, but every time the focus will be different. And today's focus will be building a general purpose assistant in the visual world. And this might sound, too abstract. Then I use a different subtitle, which is to building and surpassing GPT-4 or multimodal GPT-4. This is more concrete, right? Since March last year, and the community have seen the amazing result of the OpenAI GPT-4 model. And I think everyone in the vision community and the multimodal community trying to, catch up and learn how they actually build such a model and how the community can, do a better job in building a visual system. In today's presentation, we will mainly focus on an open source project that the team and me have been focusing on in the past 1 year, and it is LLaVA. Okay, and before we start, I'll introduce today's agenda. I'll first talk about the topic, computer vision in the wild, which is the topic that we're trying to solve in the past 3 or 4 years. And in the second part, I'll talk about the basic LLaVA and how we build the data and build the model. In the third part, we will extend the basic model into different variants. I'll talk about the different variants from the 3 perspectives, including application, new capability, and the performance. Okay, let's start with the computer vision in the wild. The definition, the one-sentence summary is we want to build a transferable foundation model system that can easily adapt to a large range of visual tasks in the wild. Think about this. For any task that we humans may have that involves images, videos, and we want to have a system that can directly solve this problem without model tuning, without any training examples in the real life scenarios. And this is what we mean by computer vision in the wild. And to have a more concrete definition, and emphasize 2 aspects, 2 key factors when building such a system. One is the task scenario that we want to consider is really broad. Think about any computer vision problem. The second part is when we trying to adapt our trained model into these scenarios, and we hope that the transfer cost is low. And in the ideal case, or in the extreme case, that it means that we don't want to train the model again, and we don't need any training data. And this is very similar to what the current GPT-4 type of model has achieved. And if you want to learn more about the definition and the more literature of computer vision in the wild, and please check out the GitHub link and the YouTube link. And these are 3 standard classic visual recognition tasks, including image classification, object detection, and segmentation. So they both, to me, that they are the image to text task, but they are implemented at a different level. Image classification is implemented at the image level, and object detection is to recognize regions instead of the entire image. While segmentation is even one more step, even more fine-grained. Think about the pixel level, right? And so if you think about any visual recognition problem, eventually it is an image to text problem. So I think these are examples to illustrate that one sentence that we always use when we build such models, which is, every visual recognition problem is essentially a vision language task. And so in this slide, I'll quickly summarize the work that we have done in before LLaVA. As I mentioned before, that we could easily consider, most of the visual understanding tasks and the image to language task, and then I'll provide 3 different perspectives to illustrate this. to further introduce the work that we have done. The first perspective is data view. So here we mainly consider about the public data. And so there is a trade-off between the amount of the public data and the richness of the semantics that is contained in the data. So we can see that in this data spectrum, we start with image data or the pure vision data only, and there is almost infinite amount of data over there, right? That is why vision self-supervised learning became popular, and because of this, promise. And the issue is there is no semantic associated with the vision data itself, and then we can see that gradually from the image level to the region level and even to the pixel level, and people gradually allocate more human related semantics on the visual data, but because of the cost of the annotation, and we see gradually the amount of the data it's become less and less. Okay. In the second perspective, the modeling perspective, here I summarize some of the work that we have done on the open set recognition. And last one is the benchmark, because our goal is to build a one foundation model so that all one foundation system, so that once the system is built, and we hope that the system can directly solve a large range of different vision tasks. But when we started, we noticed that there's no unifying benchmark to evaluate the progress. That is why we organize challenge and workshops to trying to have people to evaluate their models on the same benchmark. So all of this, they have been done before 2024, and they are mainly focused on contrasting models, right? And this year, we will organizing the workshop again, and it's in Seattle. It's local to me. And in this year, we will be focusing on models more similar to GPT-4V or similar to LLaVA. And so this is more like today's subtitle, right? Building general purpose visual assistant, and we hope to have a language model to combined with a different visual expert trying to build an assistant that can really achieve computer vision in the wild. And if you have any feedback or anything that we should include in this workshop, please feel free to reach out. And know that we still call for paper and call for challenge submissions. Okay, and all of them everything that I have introduced now about is about image understanding, and this is the conversion from the image language. I also want to show the reverse process, image generation, which I believe is the reverse problem of image understanding, where we trying to convert language into visual data, including images and videos. Now, I will not dive into visual generation in this topic. In this presentation, I mainly use image understanding, the conversion from the image to the language as the illustrative examples in my presentation today. Okay, the second part, the first LLaVA that we have started to build in last March. Now it is just 1 year. And the work was released on April maybe 16 last year, and we spent 3 or 4 weeks to build the LLaVA from scratch. Now it is almost 1 year, and so I'll start to illustrate to talk about the background, why we want to build LLaVA. Right, and when we look at this, is mainly motivated from the literature in the NLP community, and this is my summarization of the OpenAI models. And in each generation of the models, they not only inherit the previous nice properties of the LLM, they also trying to have a new nice properties. For example, moving from the GPT-3 to ChatGPT, and the nice property is instruction following, right? And moving to GPT-4, the nice and unique property is, the model is able to accept visual input, right, including images. And these two are unique, properties in their neural generation of models. And this is something that I think the community should want to have, right? And indeed, in the open source community, and we see the release of LLaMA, and quickly people build Alpaca and Vicuna in the open source community, right? And which is trying to replicate ChatGPT, with some small cost or affordable cost, right? And in our group, we also want to make contribution to the open source community. And more specifically, I talk about two projects. One is instruction tuning with GPT-4, where we're trying to build the instruction tuned language model with GPT-4. And motivated from our success in language domain, and then we move into the multimodal domain, which is actually, largely laid the foundation for the LLaVA project. Let's start with the first one. Oh, sorry. So I want to emphasize that all of this project, because as you may gradually realize that the models almost remains the same, right? For like not only OpenAI models, but also the open source models. So the focus of all this work is really data, right? So I would call this like data-centric AI, not model-centric AI. Okay, the first work, instruction tuning with GPT-4, and this is mainly relying on the framework called self-instruct, right? Now we write down a handful of examples, and then we ask a language model, strong language model, to try to create more examples, and this is how we construct the instruction following data in the language domain. And when we started, we see the base model, LLaMA, which is open source, and we also see the work of Alpaca, right? But Alpaca was trying to run the self-instruct framework using GPT 3.5, and we at Microsoft, and we get more familiar with GPT-4, and I was thinking, is it possible that we can run the self-instruct framework using GPT-4? And this is not only a good opportunity for me to learn GPT-4 API or model itself, but also, I think a useful, learning to summarize for the community. And this is what we have actually done in the first project, instruction tuned with GPT-4. And eventually in this project, by running self-instruct framework using GPT-4, we are able to create a data set for language instruction following. And we also trying to use GPT-4 to create the feedback data, where we can, ask GPT-4 to rank the quality of different responses for given questions. And based on this ranking data, we can train a reward model. And let me quickly summarize the learnings in that language-based project. The first one is using GPT-4. We really achieve better results compared with GPT 3.5. This is no surprise if you look back today. And the second one is, GPT-4 is really can really provide consistent feedback. And if we build a reward model based on the AI feedback, and we can see that this can help us to choose better decoding results. And so I think from today's perspective, there's no surprise in this project at all. But to me, I think because this is really, the first time that we used the GPT-4 and to learn GPT-4 and show that the great job that GPT-4 is able to do. And so after this project, now we can see that with GPT-4, and we are able to build the instruction tuned language model in the language domain, right? But when we look at multimodal domain, and we surprisingly found that there's no notion called instruction tuning in computer vision or in vision language multimodal community. And me as a researcher who have been working on the vision language domain, for a long time, and I found that this is I think the most fascinating thing to do at that time, March last year. So that's why, with this foundation, and we trying to, bring the learnings experience that we have in the language domain to the vision language domain. So still, we want to use the self-instruct framework as people in the language domain has done. But one immediate challenge is, and there's no teacher, right? And so think about this. We are going to build, GPT-4V, right? Or multimodal models, which means that it is like in the input part, we have the image as part of input, and for the output, we have a text, right? But if you look at our teacher models, back in March last year, and there's no GPT-4V yet, right? We only have the language model GPT-4. And now you may notice that there is an inconsistency, right, between the teacher and the student. And that this is the one unique challenge that we have met when we build the LLaVA model. And so I think the unique challenge is how could we represent the images so that the language model can understand, right, when we create the visual instruction following data. So to solve this unique challenge, we were thinking, for in the community, in the computer vision community, we have lots of powerful image understanding tools, right? And the results of this image understanding tools is to provide annotations, right? For example, giving an image, if we do not want to use the pixel level representation of the raw image, instead, we have like the annotations. For example, we have captions which trying to describe the image from different perspectives. We have bounding boxes which trying to locate the key objects and represent them using coordinates and the key concept and or key object, right? So captions and bounding boxes, even though they are not the perfect representation of the original image, and of course they are for sure that they will lose some information of the original image, right? But I would say that they are good approximations of the original image. So, and the nice property of this representation is, now they are really symbolic representations which can be organized into a text sequence, right? And note that GPT-4 can accept the text sequence. So that's why, instead of using the raw pixels, we will use these two type of representations, symbolic representations as an image representation and feed it into a language model such as GPT-4 to run the self-instruct framework. And following the same self-instruct framework in language domain that we are able to create the first visual instruction following data set in the community. And more specifically, we consider three types of instruction following data. The first one is multi-turn QA. And given this image, think about we will talk about the basic concepts or objects or the attributes of the image itself. For example, the color, the position of the objects, right? And second one is detailed description, and we will ask the model, to generate the description of the image as detailed as possible. And last one is complex reasoning. Instead of talking about the content of the image itself, we hope the model can do some reasoning or implication of the image. For example, in the image provided here, and the question is, what challenges do these people face? And so the answer is, there is a small SUV and there are many luggages on the ground, and the unique challenge is how we could actually pack these luggages into the small SUV, right? You may immediately notice that this is not only about the content of the image. This is about the implications that we people can reason about the image, right? So this is the instruction following data we create in LLaVA 1.0. This is also now called LLaVA 158K in the community, and which is used in almost all the visual instruction tuning paper. Okay, now I'll briefly talk about the architecture and the training. So because this is data-centric AI, and we really want to keep a simple model, and more specifically in terms of architecture, we use two pre-trained model. One is a clip visual encoder, which is pre-trained, and the other one is a language model. Here we were using Vicuna. And to combine, to connect these two models, we propose a simple projection layer, which is implemented using a linear matrix. And so the goal is that, for the extracted visual features of the image, we want to use this projection layer to align the visual features with the word embedding space of the pre-trained LLM. So this is a model architecture, which is quite simple, right? And so in terms of training, we propose a two-stage training. And in stage one, we will freeze all the model parameters. We only train the simple linear projection matrix, which means that after training, the visual features will be aligned with the language model word embedding space. And you may also consider this step as, the visual tokenization, where each image will be represented as a sequence of visual tokens that can be understood by the language model. And in the second stage, now we will remember we built the visual instruction tuning data before, right? And now we will really run the visual instruction tuning, which means that we will further train the model on the data set that we have constructed before. And here we will update the language model and the projection layer. Okay, after model training, we will get a final model, which can be served to interact with the people, to accept images, and talk about the image content. And so there are lots of results. I'll just quickly summarize one result here. So we also propose a benchmark, which is called the LLaVA bench in the wild. So remember, when we started, there's no benchmark yet, right? How to evaluate those large multimodal models remains unknown. And we were able to quickly come up with our own evaluation benchmark, and which only contain less than 100 examples. The good thing is we can quickly evaluate the quality of the models. And turns out, compared with the earlier commercial models, and our simple model performs like comparable or not that bad, right? Note that this is not really rigorous, because this is only evaluated on like less than 100 examples. Okay, now here are some examples. So I promised to you that our goal is really to replicate some of the interesting examples or nice properties of GPT-4V, right? And this is the example, the popular example that is showed in the GPT-4 paper. And so the question is, what is unusual about the image? And we say that both GPT-4V and our model is able to illustrate the reasons on like what is unusual, because you can see that there's a man doing eye rolling, right? Eye rolling is typically an indoor activity, but now the man is doing eye rolling on a moving taxi, which is unusual. And here's another example. I will not go to details of this example, but the good thing is that we were able to replicate the second example as well. And this is the first time that in the community that we see that our model is able to reproduce those interesting examples of the GPT-4V paper. And I'll also emphasize the second nice properties of the pre-trained model, LLaVA, so which is a strong OCR capability. Note that our model is only trained on less than 1 million data, and there is no explicit and there is no OCR data in our model training at all. at least no, we didn't try to include the OCR data explicitly in our training, but it turns out the model can emerge some strong OCR capability. Let me provide some examples. In this first example, we uploaded the CVPR logo last year and asked the question, who are we interested in the content of this image? And it turns out the LLaVA model is to response and it tells that there are two group of people who might be interested in this image. One group of people is the people who are living in Vancouver, Canada, and the second group will be people who are working on AI and its applications. It means that the model can not only recognize the text CVPR, it is also able to do some simple reasoning because it's trying to link CVPR with recognize CVPR is an AI conference. A second example that I will say in about the workshop logo, and it turns out the model can recognize the entire workshop name. And last one is interesting, in the evening that we released LLaVA, I was trying to write down, the new word LLaVA on my notebook and took a picture. And turns out the model is able to recognize this new word, LLaVA itself. Okay, and I have introduced the basic LLaVA 1.0, and now it has been 1 year, right? And the community has built lots of new model variant, and we also trying to improve the model from different perspective. I'll now quickly summarize the community effort and our effort. So this is a quick plot I did in the CVPR last year. So note that the foundation is the open source LLaMA model, and the inspiration I think always starts from the DeepMind Flamingo paper. And in April 16, and we propose the LLaVA model, and meanwhile there's a concurrent work called the mini GPT-4, right? And we see that quickly there is a large amount of a large number of papers appears and on this topic, and most of them are about new models, and some of them are about the benchmarks. And gradually there are more and more projects on this topic, and I believe that there are even more papers after June last year. I will not show it here. Okay, and on this slide, I'll summarize the milestones that we have worked on the LLaVA project. And more specifically, I'll talk about 4 projects which are summarized in 3 perspectives. The first one is LLaVA, which is the illustration of the applications of the LLaVA model. And second one, is the new capabilities that we could enable based on the LLaVA model. I'll use LLaVA Interactive and the LLaVA Plus to illustrate the ideas. And lastly, I'll talk about LLaVA 1.5 and the recent LLaVA Next, which illustrate that how we continue to improve the performance that is trying to catch up the GPT-4V performance. Okay, the first one, the application. So remember that the LLaVA model is trained on the web, on the image text pairs from the web, right? And this is a model that's trained on the general domain. But there are many interesting vertical domains, including gaming and medical, or healthcare, right? And so I immediately say, and it raises a question that how we can, adapt the general domain LLaVA into the vertical domains, for example, healthcare, right? And so we collaborated with the Microsoft healthcare team and trying to, provide a training recipe so to show people that what is the best empirical recipe to convert the general domain LLaVA into LLaVA MED. And so this is the training pipeline. And note that I list the stage 1 and stage 2 right here, which is very, very similar to the stage 1 and stage 2 that I introduced about the general domain LLaVA. But I want to emphasize that if you want to, adapt the general domain LLaVA into the vertical domains, the stage 1 is actually optional. You can skip stage 1 and direct apply stage 2, which is vertical domain instruction tuning. And in this case, we will do like the biomedical domain instruction tuning. And similar to the general domain, we will use language models such as GPT-4 to create the vertical domain instruction following data. And this is a data set that we create for the healthcare domain, right? After fine-tuning the general domain on the healthcare instruction tuning data, and we are able to get this LLaVA model. And you can compare some of the one example here. And this is very interesting. Yes, think about the entire process, right? This is very similar to how we humans actually learn a specialized domain. And so we start to learn the basic concept about the common sense, right? If we want to specialize into some professional roles, and we will learn the related subjects, right? And if you look at the behaviors are also very similar. For example, there is a medical domain, there's a medical image, and for the general domain LLaVA, it's very similar to like a person like me. I'm not trained in the medical domain. If you ask me, like, I know that this is like a medical image, right? If you ask more about the domain specific knowledge or questions, I will either hallucinate, or tell you that I don't have the knowledge to answer this question. But after tuning the model on the medical domain, you will see that the model can, at least trying to provide professional suggestions to this question and with less hallucination. Okay, the second part is about the new capability. And note that the GPT-4V model or the LLaVA model is all about image and text as the input, and the output is like a text, right? And we were thinking, how we can, build the more general multimodal models. For example, we want to include, like more multimodal interaction and a more multimodal output, right? And the LLaVA Interactive is really, a production prototype to show you that when we achieve the truly multimodal models, and what we can do, and know that there's no model training at all. It's like we combine 3 existing models, pre-trained models from our group, and show you some interesting scenarios if we achieve the true multimodal models. And more specifically, we use LLaVA for visual chat. We use Gradient model for grounded editing, and we'll use like the same model for interactive segmentation. And so after people upload an image or generate an image, and they can use these 3 different functionalities, as they need, and iterate to get the final results. Let me show you one example. Like when the user upload an image, and the user will ask what part of the image isn't visually appealing to the viewer, right? And the model will make suggestions to remove something in the lake, right? And then we humans follow the suggestion, to choose the related objects and remove them by dragging them out of the image, and then we get a new image, right? And we continue to do so, and then we get like a new image, and then we ask the model, what we can do to actually improve the visual appeal of the picture. And the model will suggest, say, that the system will suggest, say, you can actually, add some sun sign on the sky, right? And we follow the instruction to do that, and now we get a new image, and then we ask the model, about the new generated image. A model realizes that this doesn't follow common sense, right? Then there's no reflection on the lake about a sunset. And we follow this suggestion and trying to add the inflection and get a final picture, and then ask the model about suggestions. Now the system tell us that this is like a reasonable picture, and it is also visually appealing. And from this entire example, you can see that we humans can interact with the system using like a visual prompt, right, which is a multi-model interaction, which is beyond the capability of GPT-4V. And we also, the model is also, to do like segmentation and able to do editing, which is also new capabilities compared to the GPT-4V. But know that this is not one unified model. This is just like a prototype and a demo that combine like a different component and show you the possibilities, the futures. And this is another project that we conducted to show the new capabilities that we can build based on LLaVA. And more specifically, we are trying to, enable the two-use capability of the LLaVA model. Due to the interest in time, I will not go to the details. I just show you the basic concept right here. And remember for the basic LLaVA, so when there comes an instruction, the only thing that the model is able to do is to use the internalized knowledge that is trained in the model parameters to respond to the question, right? But what if the model do not have the skills or do not have the knowledge to respond to the question, and the model can hallucinate or can fail on this task, right? And so instead, we introduce a concept called, skill repository, which actually include lots of different pre-trained vision experts model in different topics or domains. And now, when there's an instruction comes in, the model can decide if the model can answer, if the model is able to answer this question directly, and then the model will respond. If it turns out the model cannot do not have the related skills, and it will try to get the related tools from the skill repository and execute it to and get to the output, and then the final output to the users will be the aggregation of the input image and the two output. And from this perspective, we can see that this can really make the LLaVA model with more capabilities or new skills to deal with the real life scenarios, right? I'll show you more real life scenarios. For example, in this example, we allow the LLaVA model to do web search and get the more rare concepts or related more grounded concepts. And we also can use the LLaVA model to rewrite the prompt for stable diffusion to get better generated images. And we will also combine different tools. For example, here we combine probably OpenSea and LLaVA to combine segmentation and the controllable generation. In here we could use LLaVA to do like combine the skills. For example, post a social media post which include not only images but also some related text. Okay, last part is the improved performance. I think for this line for research and people are more familiar with the work. The first version will be LLaVA 1.5. So the motivation that we started to do to work on this is because the LLaVA 1.0 is mainly about visual chat, right? Which is a new capability for the community. But we realized that for some of the researchers in the community, they care about the benchmark numbers. But if you only applying LLaVA 1.0 and see the benchmark numbers, and it is not good. And so, but we learn from the community and know that there people try and include the academic task related data into training, and this can largely improve the benchmark number. And this is why in LLaVA 1.5 we're also trying to include more academic related data into our training data mixture. But we know that if we're not able to do this, and there's some conflicts for the model to understand the instruction. So instead that we do some response formatting, and turns out with this new data mixture, we were able to achieve state-of-the-art across many benchmarks. And turns out that the sample our model, the sample efficiency of our model is much better than previous model. For example, we could only use like less than 100%, 100 times smaller training data set. And recently we proposed LLaVA Next, which is also called LLaVA 1.6, and the performance is further improved. And we make modifications on three perspectives. The one is we're trying to support the even higher resolution or any resolution. And we also change the data mixture, and we also include larger or better language models. And to summarize, it turns out the best LLaVA next model can outperform Gemini Pro on several related benchmarks. And it is also like the best open source model back in January with much lower training cost. And recently, we extended the capability into video. And this work has not been released yet, and we were trying to release it in within 2 weeks. When I will not dive in detail, but let's look at results. It turns out without tuning the image LLaVA on the video data at all, turns out if we do some careful inference tricks or techniques, and the image LLaVA is able to outperform all the open source video models on these benchmarks. And this is why we consider, the LLaVA Next model is a strong zero-shot video understanding model. I think here the concept of zero-shot is even more interesting. It's actually a zero-shot modality transfer, right? Because we do not train on video at all, and we can achieve the state of art on video tasks. And with this observation, and we were thinking, can we actually train the model on video data? And turns out with careful tuning, then we can further improve the performance. And turns out, and the final performance, can outperform the Gemini Ultra on, some video QA tasks. And this is the final page of my presentation. If you are interested in the related techniques, or if you want to, learn more about the basics or advances of the multimodal foundation models, please feel free to check out this tutorial in the survey. And thank you.